Getting better, but not quite finished. Talking about my flu. This is lecture 5, entitled Reducibility. Oh, by the way, it's I first spelled it with an A here, but reducibility is not a word I use much in ordinary conversation. So my initial impulse was just to spell it with an A, reducible, like undecidable and so on. No, but it's with an I. So I had to, well, you can see here, I corrected it. I had an A here before. This chapter, same thing, is part of a computer theory type course. The title of the course is called Introduction to Theory of Computation. It's a mixed senior M1, so first year masters level course. The single author of the text is Sipser, Michael Sipser, and here's a Chinese version of the text. If you're buying it in English, it would probably look like this. It's second, is it a second edition or not? I should check. Yes, it's the second edition. Okay. And okay, so this chapter will be a little bit longer than the previous one. In some ways, it's hard to compete with the previous chapter because it contained the most famous, well, a lot of people think, the most famous result in theory of computation, namely the proof of the Turing halting problem is undecidable. But there's just no way to come to a decision whether there is there is no Turing machine that can decide whether some other Turing machine with its tape will halt or not. Undecidable. Okay, so the essence of this chapter is we will prove, using a particular technique that obviously has something to do with this concept of reducibility, hence the chapter title. We'll use this technique a lot to find other examples of problems, languages, that are undecidable. We'll generate a whole string of them, and based on the undecidability of the language A suffix TM, and we will also make clear what reducibility is. I'll define the concept in a minute, but we will use this concept of reducibility we will apply it, whatever this concept is, we will apply it to the language ATM and another language, and as a result we will show that the other language is undecidable. Now after a while, you can imagine doing this, you will accumulate quite a pile of, quite a number of undecidable languages. And then you can apply the reducibility technique to those new undecidable languages and generate even more, and so on. And so it's not surprising that there's now a whole industry, an army of researchers churning out problems, or the equivalent languages if you like, problems, proving that they are unsolvable. There are all kinds of examples, including some very, what you'd think are fairly simple problems, whose solution would be desired. It'd be nice to have a solution to certain kinds of problems, because they're very practical, useful problems, but nevertheless they are undecidable. And so it's useful to know that, and hence a lot of people working on it. But it all started, well, just in this text, with the undecidability, the proof of the undecidability of a TM. And starting with that, and using this technique of reducibility, we can generate a whole bunch of other results, other languages, other problems that are undecidable. Okay? So that's sort of the essence of the chapter. That's sort of the main idea. Well, the main idea is reducibility, but well, I need to explain a minute what that is. Okay, so we will use this concept of reducibility to show a whole bunch of other problems are computationally unsolvable in the same kind of way that the language A suffix TM was unsolvable, undecidable. Okay, so put in double bar here because it's an essential definition. That tends to be my convention. Like when I go through all my textbooks and I'm preparing them, I'll put double vertical bars either side of a definition. So I'm sort of used to that. So yeah, double vertical bars either side. So here's a critical definition, sort of the essence, the main idea of the chapter 5. So what is a reduction? Well, essentially it's just a conversion of what to what. Well, a particular problem to some other problem. So when you hear the word reducibility, automatically just think in terms of two problems. Right? And you reduce one problem to another problem. So you reduce problem A to problem B. And what does that mean exactly? What does it mean to reduce? Well, it means so you reduce or convert, sort of pretty much the same, in such a way that let's say you're reducing problem A to problem B. Then the solution of problem B. So B already, you have knowledge about B, problem B. So if you reduce problem A to problem B, then the solution of B that you already know about gives you a solution to A. Okay? So which is what I've said here. So a reduction is a sort of a conversion of one problem into another. So from problem A to problem B. So the solution of the second one, so the solution of B,